Hello, everyone. Thanks for being here. So it's my great pleasure to introduce Valery Romanovski, and I'll speak about invariant and reversibility in polynomial systems of ODEs.
Okay, thank you very much for introduction. Thank Alexei for invitation to give talk on this seminar. So I will speak in this about invariance and reversibility. My topic, which I would like to address, some symmetries and polynomial invariance. I speak first of two-dimensional problem, and if I have time, I speak about three-dimensional problem. But in fact, we have a generalization of the two-dimensional result, not only on three-dimensional case, but for any area. Okay, so why we are interested in this problem? So if we consider n-dimensional system of ordinary differential equations, then one phenomena which arises in such system is so-called time reversibility. What does it mean? It means the following from geometrical point of view. If you have trajectory, then this trajectory goes in this way, but it can have phase portrait, can have some symmetry. For example, here we have a line of symmetry, and this point goes. If we make a change of coordinate x equals psi of y equals psi of x, then in new coordinates the system is the same. It's the same, vector field is the same, just appears minus between the vector field F. So it means that this point goes to this point, this point to this point, and here, for example, more complicated. This point goes to this point, this to this point. Here we still have line of symmetry, but it's possible that we have symmetry with respect to this torque. So, for example, here we have trajectory, and this point goes here, this point goes here, and this point goes here. So this is symmetry of a phase portrait of a differential system.
And this is a formal definition. Like, is there a way, like, sort of kind of way to explain it, like what it means in practice? Like what kind of real systems?
In practice, it means that often it means that the system is supposed to do.
It applies.
Yeah. From if system is time reversible, then after some sort of simple condition, additional, it has first because such systems are important. So some people say that time reversible system is system which are a bit more complicated than polynomial systems are the simplest one, and this next one in hierarchy of simplicity.
Okay. So this is kind of you will say an artificial definition.
Yes, it's geometrical definition. It's purely geometrical definition, yeah. So you see, but this also see phase portrait. For example, here you have one line, so you have nice symmetry. It can have a few lines, so it will be geometrical symmetry of trajectories. Yeah, this nice property. Here you go. So, for example, because of time limit, if you look at the first picture, because of this symmetry, so the example given by Poincaré, if you have time reversible symmetry, you can not have such damping constellations. Damping constellation because such picture cannot be symmetric. You must have such picture. Trajectory should be closed. Trajectory should be closed. So, and you, due to this phenomenon, you distinguish this important behavior.
Closed in what sense?
It's closed trajectory. Trajectory is over. It's over.
You're saying like it's not a zero set of like it's not a variety or like
it is trajectory. It's trajectory of the system. You have a system equals step of x, and this curve is trajectory. This curve is trajectory.
Yes.
So if you have time reversibility, you cannot have such. You cannot have such trajectories. All of this. So it's There are many other applications. Reversibility is one of very widely studied phenomenon. Okay, another motivation. So it's just for definition, but as I said, why it's important about this symmetries, because time reversible system have nice symmetry trajectories. Yeah, you can have mirror symmetry. Symmetry is called saddle. Yeah, you have such system of trajectories. It's called saddle. You see here you have such trajectories are symmetric with respect to this line. Yeah, but here you have if you look at this, you have this direction of time change here. -1.
I'm also a little confused about the definition. Can you go back to the definition?
Yeah.
So the f does not depend on time, right? It's not.
No, that's not.
It does not. And the minus sign is kind of like the c acts on what? C acts on the x, correct?
Yes.
And you get minus sign, and somehow that's related to time.
Yeah.
This is some
It's not
mystery.
You have ipsilon sine of x, yeah? And you just take the derivatives. So you have equals the sine for the x dot, and then you substitute here, and you have system in new coordinates. You take opposite x -1 of y. So in fact, you have make this substitution, and here you have a system in coordinates y, and that's not matter. It just is the derivative.
Yeah, but my question was, like, how is the minus related to time?
Yeah. So you see this picture. So here you have time set here. Then you do reflection, and you see time was this.
So it's kind of optically
Yeah.
you view it as.
Yeah. So if you just mirror symmetry, it should be time the same. Yeah. But you have to change time to -1. Yeah. So here you do not change time. You have this and this, and time is not changed here. After symmetry, you change time.
Okay.
Another motivation is normal forms of differential equation. Normal form is one of the main tools to study differential equations. So there are many normal forms. This study most related to so-called Poincare-Dulac normal form, but there are also some other. But Poincare-Dulac normal forms are most related to our. So if I will not explain procedure, but it's just another transformation x equals psi of y equals psi of x, another transformation, but now with the form x plus psi of the terms. And such transformation transforms the system to a simple form, which is maybe not quite simple.
No,
Yeah. So you have system which looks very simple, but if you would like to have some information, so main information which we need to study differential equations, Poincare map. So Poincare map. So if you take point, rho, you go along the trajectories, you have control. And for example, if you can here, you have a closed trajectory, and if it's isolated, then it's limit cycle. So it's main tool to study limit cycle. And if you now go to polar coordinates to first equation, let's say speak about two-dimensional case, not about this three-dimensional, but two-dimensional case. If you go to polar coordinates in such equation, simple quadratic you will not have any information. But if you go compute normal form and then go to polar coordinates, you will have exactly one power series expression of planetary map. So it's you see all information about the cycles. From this normal form, you see all information about the cycles. From this, you see nothing.
And you're saying it's normal form. How are they related? Like, are they, is there like some sort of equivalent, or like what's?
This is just a new coordinates.
New coordinates.
Yeah. So trajectories are the same, but you just introduce new coordinates.
Yeah. And so the new thing has high degrees. Did you use Grobner basis to find it? Like what's?
No. It's pure linear algebra.
But still, you still have high degrees. It can increase the degrees.
High degree in normal form.
Yeah.
Yeah. It's actually it will be infinite.
Oh, because it's you just cut it.
Yeah.
It goes there's expansion.
Yes, it's expansion, infinite expansion. So you have simple, but then you have infinite. But it's simple. Yeah. Okay. So and to show that interesting fact about this coefficient, if you now look for this coefficients which appears here, it turns out they are invariant polynomial invariant of certain group action, which I will explain later. So invariant not in the sense of some people often call invariant first integrals. Yeah, some people do not make a special PDEs. They mean by invariance first integral, but here invariance in the classical sense which Hilbert studied polynomial theory of polynomial invariance, where was very popular by the beginning of 20th century. So it's this ones. So we will give an algorithm to compute basis of invariance which such this polynomials which monomials which appears here. And then we show interconnection of the invariance and integrability. And as I said already, integrability, if we consider n-dimensional system, for example, in the book of Bilka, you can see that if your matrix has 1 minus 1, and then we have another so matrix is diagonal of such form, then system has at least one analytic first integral of such form in the neighborhood of the origin. And this known result, but recently, relatively recently, in this paper by Liebler, Batazzi, and Blocher, and then also Blocher maybe first appears here, it was proved that if vector field X system under linear transformation, if was a vector field after linear transformation, we have this equation. So instead of minus 1, we now have zeta. Zeta is the difference. Zeta is primitive root of infinity. Then under certain condition, all first integrals of linear system are conserved. That is, if this monomial is first integral of linear system, then that nonlinear system has analytic first integral of such form. Okay, I will first speak about two-dimensional case. So we study system in such form. The form of the system is important. So here we have a polynomial system. We have finite number of parameters, finite number of terms, and if you have 10x plus 1 plus x plus 1 y to the cube, then coefficients will not exist. In the second equation, coefficient of such monomial is denoted in this way. This is the set of indices GPS is the first equation, and the second is conjugate as it says we have PQ, then here we have to be just evolution.
So Lotka Voltaire would be the simplest example, right?
Yeah, Lotka Voltaire will be simplest example because in the case of Lotka Voltaire, we do not need here -1. Okay, so this interconnection of time reversibilities and one parametric group of functions studied by Sibirsky, Liu, and Lee, some others. I will go further. Yeah, so I recall what is polynomial invariant. We have some field K, then we have some group of general linear group, and for matrix A and any vector K, then Ax just usual action, and polynomial f is invariant under the action of group G if f of x equals f of Ax for all R from the group. Yeah. So this is classical definition. Okay, in fact, we will study in the place that we have here I, but it doesn't matter. We have just studied invariance of this group. So what is this group? In fact, this is quite interesting, but maybe here it will be not visible. Okay, so we have such action. You just made rotation of some case set transformation of the phase space. Yeah, so it's just simple transformation. But if you do this change of coordinates, you have system in new coordinates, and the parameters now are changed. And it turns out that changed by simple law. By simple law that we have now diagonal matrix. So in fact, we have a representation of our group 4 in this space C2A. Yeah, you agree? Okay, and this is in diagonal matrix here, just diagonal matrix. These numbers are on the diagonal. Okay, so again, it's our system. Now we have first equation has A coefficients, second has A coefficients, so altogether we have 2A parameters, and we just denote an tuple by nu. This is an tuple of from here. For a given order set, we do the following. So we just write down, so we take first coefficient AQ right here. Then we have next coefficient right here. The last one will be AQA with sub indexes of the first equation. And then we at the second equation, which uses involution. So we have PAQ, so here we just have QA, and so on. Here was Q1, it will be Q1 P1. And now we consider the set. The set of all new sizes and new equal K. So it's obviously it will be abelian monolith. You agree?
I'm just trying to read it.
Yeah. So just write this coefficients here, some indexes, subscripts, first subscript, second, and so on. Then for the second equation, and then we have such linear operator. This is linear operator acting on this.
How does L new end up in Z2? Am I just reading as well?
Sorry?
These coefficients, are these coefficients, what do you call it, binomials, or is it a different notation?
It's a tuple, I think.
It's a tuple.
No, yeah, it's so
Tuple multiplied by number V1. V1 is an integer.
Right.
Each of them is an integer, so
Yeah,
you multiply a couple by
Yes.
integer.
Okay. So it's linear model. Yeah.
So L depends on V, correct?
New.
New. Okay, so L depends on new.
Yeah. L of new. Yeah.
Oh, you're right about that. L of new.
Yeah.
Oh, yeah, that makes sense.
L of new. And if you have this, then you will have also such solutions will be such will be satisfied. Obviously, with the monoid. Okay. So now we have fixed this entuple. We have fixed all this operator of new, and now we just write all coefficients of our first equation, and then conjugate equation, then coefficient parameters of the second equations. This one's first and this one. We have a L here and we have L here. So we have N monomial is of such form, yeah. And we do not write this, okay, but just write exponent, and we denote this exponent by mu. It's okay, yeah. Okay, and the main important result, which we prove by Sibirsky, that monomial mu is invariant of this group 4, if and only if this mu is from this monoid. From this monoid, if nu is from this monoid. So we have to find Hilbert basis of the monoid. Yeah. To describe all the invariants, we have to find the Hilbert basis of the monoid. But Sibirsky did not provide any algorithm to find this. Actually, he did it by sorting. But efficient algorithm was proposed in our work with Girach and Laubenbacher. And now, yeah, so when we have nu, we take involution of the entuple nu. Yeah, this is just involution. Nu was this one, and we take involution, so this goes here, this goes here, and so on. So it's now involution, yeah. And if you consider such binomial ideal, this ideal where we can take mu from monoid and minus this conjugate. We have ideal which is called Sibirsky ideal of system 3.
Could you show me the slide again?
Sorry?
Could you show the slide before?
So we just write exponents here. Instead of writing the whole this monomial, we write just exponents. Okay. And in fact, it was proved that the variety of the Sibirsky ideal is the Zariski closure of the set of all systems which are time reversible with respect to such linear involution. So this is if you make this exchange of coordinate, but here you have x goes to alpha y goes to alpha minus 1 to x. It also proved that all systems whose parameters belong to this variety are local analytically integrable. It means they have analytic first integral in some neighborhood of the origin.
But you could, so you say like with respect to this particular linear transformation, but it could be many other.
Yes, it could be some other transformation. Usually they look for involutions in two-dimensional case, but in three-dimensional case, transformations usually which make sense are permutations.
But can you do something general here, like any kind of transformation, and then go back and introduce your thing?
Yeah, we can, but it's quite
and maybe useless.
Yeah, interesting is maybe useless because we did a lot of work, but not really interesting results there.
But this is
This is linear. Yeah, you see, the nature is quite like simple things. Okay. Yeah. Yeah, maybe once last slide from the introduction. So we have again, this is our we are interested in invariance of such group of transformations. So it's a group of transformations, but reversibility is related to this group of transformation. And how they connected? They connect in such ways. If you have this matrix, which is from one side is involution, but from the other side is permutation matrix, and you take diagonalization. Then the diagonalization is this matrix, and this group is just a Lie group generated by this. So it's the Lie group E to the A to V. So this and so this group gives rise to this transformation. Similar both in a higher dimensional case. We have permutation matrix, we take the diagonalization, and then we study invariance of correspondent similar group, and they are, it turns out they connected to reversibility. So reversibility with respect, we will see that reversibility with respect to cyclic permutation group with its integrability. Okay, and now I present algorithm how to compute Hilbert basis of this invariance. So algorithm actually we based on the algorithm from the book of Sturmfis. Are you familiar with binomial ideals? Binomial ideals.
I think an introduction.
Yeah. Okay, so it's just we have C algebra. So we are given matrix. First we give some matrix. A is not our matrix, but just any matrix. Yeah, matrix is N to D matrix. Then we have a group of variables T, group of variables X, and Y1. It's variables with fixed elimination monomial order. On this way, consider C algebra homomorphism to the Laurent polynomial rings, and this is polynomial map. It's X I goes to Y, and this is comes from you take column of your matrix, and you write down this product, and Y goes to Y I, and then by the algorithm of Sturmfis, algorithm invariance theory, if you are interested in such monoid, is a bit different from others. So it's just you have matrix times nu. This also will be monoid, yeah. And here the basis of this monoid is obtained using simple algorithm. You just compute reduced Grobner basis of such binomials, and then Hilbert basis of this MA consists of all vectors nu such that it will be many other binomials, but you take just binomials of such form, which depends on X and Y, but not on T, And then these exponents will give you a Hilbert basis of this monomial. And we can use this algorithm for our problem. You see that in our case, we have linear map, but now we have KK. So we cannot use it directly. This is something, but if you subtract from the first equation the second one, you have just such equation. So you have one dimension matrix here, this matrix, and you can apply the algorithm from Sturmfis. In the following way that you compute this algorithm of Sturmfis, you compute ideal. So you form such matrix, but in our case, then you compute some Grobner basis, and from this Grobner basis you can read Hilbert basis. I will not go to the data, but I will now mention some interesting algebraic properties of this Sibirsk. So it's our ideal, and this is fractal A, PDN matrix. Then we can define the algebra homomorphism in such way by this simple polynomial map. Then image of this the K algebra is denoted by in this way and called toric ring, but Kerner is denoted by I to the I, it calls the toric ideal of Y. So this study is very closely connected to toric ideals. So in our case, we have such matrix, but our matrix, we can compute of course toric ideal of this matrix, but it does not have a sense from any meaning from the point of view of differential equation. What we will see later, what is meaningful. And now another thing for this field K, we denote by K of X polynomial ring, and for subgroup, any subgroup of Z to the N is called lattice, and for theta from Z we can write every vector such that we take positive and negative coordinates. So we can decompose such that here we have only positive coordinates, and here we also have only positive coordinates because here we have minus. And then we can write corresponding binomial x to the c plus, x to the theta minus. And this idea now generated by such binomials is called lattice idea of this lattice. So it turns out that Sibirsky ideal is a lattice ideal because this lattice, if we take this set, or this is n tuple minus conjugate n tuple, then this will be subgroup of Zn. It's easy to see, and we now denote corresponding lattice, this lattice by IL, by L, so this corresponding ideal. So we have theorems that Sibirsky ideal is lattice ideal, more precisely for this lattice. For this lattice where nu goes through M. In fact, another important thing is Lorentz lifting of integer matrix is obtained in this way. So we just write our matrix A, but then it's identity matrix, and once again identity matrix. So the algorithm of Sturfis is just computes toric ideal of this matrix, and which we have used. But now let's go to reversibility. Condition from the equation from my first slide. If you apply equation of the first slide, this definition, you can derive the conditions of time reversibility is given by these equations. And the set of all time reversible system is subset of the variety of the first elimination ideal. So we just have to eliminate alpha from this binomial ideal. And theorem, this elimination ideal is denoted by I, and this just ideal gives us time reversible systems, this I. So theorem says that Y is this, and this ideal is kernel of the polynomial map defined in this way, And if you look, compare it with Lorentz lifting will be this one, but what we have here, we have another lifting, which is defined this way. So here it should be not 2L, but should be L, IL, I tilde L. So it's matrix having one is just identity matrix, and this is so here matrix such, and here once such way. And theorem is that Sibirsky ideal is equal to the reversibility ideal and equal to the ideal IB, toric ideal of this matrix. Okay, so here is maybe example. You can see our simple quadratic system and what we can compute here. So with our algorithm, we can compute this matrix factor M, and then we can compute corresponding historic ideal of this vector, but which is I have said it's meaningless. But then we compute Lagrange lifting of this matrix, and this is Lagrange lifting. And now you take from this lifting, for example, this monomial, then this monomial, and so on. And from this you get Hilbert basis of our monoid M. And as to reversibility, so here we obtain now Hilbert basis. So from such monomials, we just write down exponent. Exponent of this is just 1, 1. Exponent of this is 1, 1, 0. So it will be Hilbert basis of the monoid. And now to compute reversibility, we compute reversibility ideal. We use this binomial ideal, and then we now eliminate T1, Y1, Y6, and obtain the same ideal as IX. It should be as it should be by our theorem. And I will say a few words about three-dimensional case, and the dimensional case is similar. So in this case, we have matrix linear path will be 1 zeta well times x y zeta with linear approximation. So here parameters now p.
For the two-dimensional case, it's all done. There's nothing there to have to do.
Yeah, because I think it's done here. But
In an interesting way, like for the interesting.
yes, two-dimensional case done. And now we did n-dimensional case also. But you can, in this case, which we studied, the matrix. So if we consider x dot ax n-dimensional case, we consider on the case when the system has exactly one first integral, but it can have many, and this is open.
Okay, so yes,
It's open to work. But so it's the simplest high-dimensional case.
by the way, was it surprising to you that this property is described by polynomial equations in the parameters?
Yes, it's I think it's quite surprised. Yeah.
It's surprising.
Yeah. So it's with my point of view, it's a very, very interesting problem. It's many open problems here. Also, I just mentioned maybe that here we have permutation matrix, as I said, this one, three-dimensional. Then we have a diagonal matrix. It will be 1 zeta zeta, and then we study invariants similar of this word of this form. And then I said now we have a generalization of time reversibility by Walker and other. This here is that of -1, we have theta. And yeah, it's by Lieber, Matas, and Walker. And what we can introduce something like Sibirsky ideal, which I will not go to the details, but again we have similar conditions. And now we defined ideal which describes reversibility. We describe reversibility, and now we have, I think, a very beautiful result. In two-dimensional case, it was we have result that this ideal describes invariant. This ideal describes time reversibility. And in two-dimensional case, they were equal. But in three-dimensional case, in high-dimensional case, they are not equal. but related by this very nice algebraic, simple algebraic conditions. So it's, I think, the main result. This study. Okay, I think I will stop here.
Thank you.
So I think it's very, very cool. I like this result very much.
Looks nice.
Yeah, it's very nice.
All right. Thanks for the talk. So do we have any questions, Valery?
What are the next?
Next step here, I think, take, for example, matrix when we have this has two integrals.
Yeah.
Yeah, and
study that.
study what happens. Yeah. It looks, I think it's possible to work, but it's not straightforward. I don't see it straightforward, but something similar should be. But it very much depends on the structure of. So you have to find actual. Yeah. So you have here. If you take eigenvalues of this matrix, you have to consider equation lambda 1, lambda n, so it will times, let's say, nu equals 0, so you have it's scalar product, yeah, scalar product, dot product, yeah, dot product, and you have to find a nu which satisfies this equation. Then this nu will define first integrals. So every thing will very much depend on the structure of eigenvalues of matrix.
And knowing that there is a first integral lets you actually find it, right? So if you go just like exhaustive search by degrees.
You mean to find first integral in?
Yes.
In
Just to,
no, we just prove that it exists.
but then, like, how can you use this?
Okay, if you, but it's quite useful. But if you, okay, first maybe you, if you know it exists, you just can try to compute up to
All degrees.
Up to
All degrees. You can actually go all degrees since you have to since it exists, you'll find it eventually.
Here is a problem.
Oh,
So yeah, we can find using so-called Darboux methods. So, but using some Darboux methods, we look for invariant surfaces, and then with these invariant surfaces, we can find exactly in the closed form first integral. Yeah, but it turns out this case when it's time reversible, it's easy to prove that it exists, but very difficult to prove to find closed form.
ah, right. So because you're not talking about polynomial rational, you're talking about like any like analytic something.
Yes.
Okay.
We're talking about analytic. Yeah. So it's in this case, it's easier to prove that it exists, but very difficult to find closed form.
Thank you.
Do we have any questions? If not, let us thank Valery again for the great talk.
Thank you.